I'm Andreas Rumpf, and I'm here to show you the metaprogramming capabilities of the programming language Nimrod, which I designed in my spare time, because I could. So how is this talk structured? First, I will explain Nimrod in a single sentence. Then I'll talk about some of its notable features and its implementation aspects. Then we'll see nothing but code, the famous Hello World example with some twists, of course. Then I'll show Nimrod's macros features. Then we'll optimize Hello World with Nimrod's term rewriting macros. So we're going to optimize the heck out of Hello World. And then I have another example for term rewriting macros called hoisting. And then I'll give a summary about what you've seen in this talk and about what I had to leave out. Okay, so what is Nimrod? Nimrod is a statically typed systems programming language with a clean syntax and strong metaprogramming capabilities. And in the snippets here, you can see that we have attained mode, that we support systems programming with a bitcast feature. You can easily define your own iterators thanks to the yield statement that looks comparable to C# solution, but in fact works quite differently. And in the last line, you can see the actual definition of the unequals operator in Nimrod. So the unequals operator simply delegates its work to the equals operator and calls not on it. And this works on a very general type here called expression. So you never have to implement your own unequals operator. You simply have to implement your own equals operator, and then the unequals is available thanks to this macro. The template is a declarative macro, and we also have imperative macros. I'll come to that later. Okay, some of its features. We compile to C and a large subset of the language to JavaScript. We also support C++ and Objective-C code generation for easier interfacing with these languages. We have a real-time GC with maximum pause times of about 1 to 2 milliseconds in the test that I did with it. And I think it's ready for commercial game engines, but we'll see. The compiler itself and all of the standard library, and that includes the GC, are written in Nimrod. And the compiler also performs whole program dead code elimination for us. So everything that you don't use is not included in the final executable. And our standard library is written with this in mind. For instance, the parsers that we provide don't use regular expressions. So if you use our parsers, your code does not become dependent on a regular expression engine. And by the way, using regular expressions for parsing is misguided anyway. Yeah, the GC is also optimized the way if you do not use it, but you can also say explicitly that you don't want to use it. Yeah, it's a bit off the screenshot, I'm sorry. Our whole infrastructure is also written in Nimrod. We have an IDE called Aporia. We have a build farm. We have build tools, package manager, and forum software. And the compiler supports an IDE mode, so your favorite text editor can query our compiler for code suggestions, as you can see on the screenshot here. And it works. Okay, now finally some code. This is the famous Hello World. I added the 99 here to have it a bit easier to explain what happens. Now, obviously, that produces Hello World 99, but how does it work? Actually, the echo is declared as a procedure, which is Nimrod's word for function. And it takes a variable number of arguments and applies the dollar operator on every argument, yielding a string. So the dollar is Nimrod's toString operator. And the var arguments mean that the arguments are gathered into an array, and the square brackets denote an array. This is a local type converter, so only in this echo context everything is converted to a string for you. And in contrast to C# or Java solution, that does not require any dynamic binding whatsoever, and also it doesn't imply downcasting to object or something like that. And yet it's still extensible. Here we have a custom type myObject and declare the dollar for it. Just delegate it to the field s of x. Then we declare an object with the value x, y, z, and echo it, and it works. So the dollar in the var args declaration actually refers to an open set of overloaded symbols here, and that's quite an important feature of the language. Okay. Nimrod's focus is on metaprogramming. We use macros to avoid code duplication boilerplate. Here in this example, I declare a macro in line 1 called HTML tag. That takes a tag name and produces a function of that name, and the function simply returns its name as a string in angle brackets. So here, the ampersand is Nimrod's concatenation operator, and AST to string is a built-in that transforms the AST to a string, and in this case, it transforms the procedure name into its string literal. Now, then we declare two procedures, BR and HTML, in line 4 and 5. And finally, we use that BR procedure in line 7, so it produces the BR in angle brackets. And now, the ordinary macros and templates participate in overloading resolution in Nimrod, but immediate macros do not. And so here we use the immediate because the BR and HTML identifiers are undeclared at the point of the invocation of this macro. And so the compiler doesn't try to infer a type for BR or HTML, which can only fail because these are undeclared identifiers. Okay. We use macros for control flow abstraction. Here I declare a macro once that takes a body of code. So the body of code is passed via the colon indentation in line 8, 9 and line 13, 14 to it. And it ensures that this piece of code is run exactly once. So this produces the first call of P, some call of P, then new instantiation, and then some call of P. So the once template performs its magic with a global variable x that is a guard, and the global here refers to the lifetime of the variable and not to its scope. That's pretty important. And the x is it is a hygienic macro, so the x cannot be used outside the once macro and also cannot be used in the body that is passed to it. And now if we would have instead a top-level variable x, that would be an ordinary global variable, and it would have a global scope in addition to the global lifetime. So this example here shows that the x is, there's a new fresh x produced for every instantiation. So as you can see, P only executes once the first call of P, but if we do pass another thing in line 14, new instantiation, then it still produces this code because the variable x is duplicated. Okay. We use macros for lazy evaluation purposes. This is the famous logging example in Nimrod. Here the message parameter is evaluated in a lazy fashion. And so if debug is set to false someday, the expensive string concatenations or to string operations in line 5 won't be performed. So ordinary function evaluation, I mean the argument passing is eager, but for templates it's lazy. Okay. We use macros to implement DSLs, domain-specific languages. Here we declare an HTML generator of the name main page, and then it has a head and a title and body, UL, LI tags. And then we execute this main page generator, and this produces the HTML code that you can see here. And now I'm going to show how this is implemented. Again, we have a couple of templates. In line 1, the HTML template declares our generating prog. So it takes the name of the procedure and the statement, a list of statements that's inserted into the body in line 4. And we start with setting the result variable to the open HTML tag. Then we perform the steps that are passed to it, and then we append the closing HTML tag. And the result is a special variable in Nimrod that represents the return value, so there's no need to have a return result as a final statement here. Now the nested tag template is a template that produces a template of name tag. And again, we simply append to result the tag name, then we insert the statements, and then we append the closing tag. And a simple tag in line 13 is quite the same, except that it doesn't take a statement list, but a single expression instead. And with the help of Nimrod's percent operator, we produce a soup of tags and angle brackets. So the substring $1 and $2 in line 15 are replaced with their corresponding arguments here. And then these meta templates are used to declare the final templates, which are body, head, UL, title, and LI. So after a first round of macro expansion, this code is produced here. And I think it should be pretty obvious by now how this works. So this DSL is actually translated into a single procedure main page that does some pretty boring stuff, in fact. It's just a couple of string concatenations and string formatting operations. And now, if we invoke this procedure main page, the compiler recognizes that this is side effect free and evaluates it at compile time. So this is all optimized into this long string literal here. Yeah. We use metaprogramming to provide user-defined optimizations via Nimrod's term rewriting macro feature. Now we've seen that compile time function evaluation already helps quite a lot, but sometimes it can fail, and I'll show how. So back to the hello world example. Here we declare a type myObject with 2 integer fields a and b and a string field s. Then we produce a value of it with the values 3, 4, and abc respectively. And then we again simply echo it. And again, now this time it uses Nimrod's built-in dollar operator for object, which is declared in Nimrod system module, which is quite like Haskell's prelude. Yeah, so this time there is no overwritten dollar that could be invoked instead. Okay, the implementation of the dollar operator for our ordinary objects looks like this. So we have a generic here in line 2, a generic type t, and the colon object is a generic type constraint. So this is the dollar for every type t that happens to be an object. And again, it's pretty much straightforward code, except that we rely on a built-in field pairs iterator for this to work. So the field pairs iterator takes an object, and yields the field name and its corresponding value. What? Oh no. Okay. The built-in fields iterator transforms the for loop into the following. And so it unrolls the loop at compile time. And now the task is to optimize that code as far as possible. And the desired result here is this thing. So it's a single concatenation where everything has been evaluated as far as possible. And note that the object A, object.b stuff is not known at compile time. So we can't do anything further with that. Okay, to eliminate the percent operator, we want to evaluate it partially. And so let's have a look at the implementation of the percent operator. Again, this passes the format string f with the help of a local variable I in line 3. And then it appends either f at position I in line 16, or it appends the passed argument in line 12, a at position j-1. Okay, so and now we transform that into a term rewriting macro. Here we can't use a declarative approach, but instead use an imperative approach, so it's a macro and not a template. And here we match against the pattern, and the pattern is given the curlies in line 1. And so the pattern reads it's an invocation of the percent for f and a, where f is a string literal and a is the array of strings. Now here the important thing is that f is a string literal, so it's known at compile time, and so we can perform the partial evaluation. So the macro here transforms the matched pattern into an AST, and the AST is a single call expression of the ampersand in line 2, and here we either append the character literal f at position I in line 16, or we append the a at position j-1 in line 12. And again, here we operate not on strings, but on AST nodes. Okay, so this implements this optimization, and this produces the following result. And now, thankfully, the compiler performs a variant of constant folding for us, producing this instead, so some concatenations have been eliminated. And now all that's left to do for us is to eliminate the add operations. And again, we do this with Nimrod's term rewriting. Here the optimization rules are simple enough that we can use a declarative approach. So we have two rules, opt at 1 and opt at 2. And the rule opt at 1 reads x is assigned y, and then set is appended, where we can transform that into x becomes y concatenated with set. The second rule is similar, but I'll skip it now. And by the way, the names for the term rewriting macros are only here so that we can disable it easily, because these optimizations turn out to be tricky and buggy. Okay, so how does it work? The orange line is matched against the orange part of the pattern, the yellow line against the yellow part, and this is then transformed into a single assignment, the blue stuff, and then the rule applies again and produces an even longer assignment, and it goes on until every single add expression has been eliminated. Now we still have some nested concatenations here, but thankfully the compiler performs constant folding again, and it produces the final result that we wanted. So everything has been eliminated as far as possible. Now the implementation of the percent on the opt format optimizer looks suspiciously alike. Can we perhaps avoid the code duplication? Yes, of course. it looks like this. And here the common implementation has been extracted into a format implement template, which has been parameterized because we either need to do nothing with the character or we need to transform it into a character literal. So it's either it operates again on strings or on AST nodes. And to do nothing, we pass the identity template in line 19 to it. So identity is simply another template that doesn't do anything with its X. And yeah, as you can see in the other case, in line 22, the new literal function is passed to it. Okay, so I've now yet another example for Nimrod's term rewriting macros. Here in line 13 till 15, we iterate over every line in the file input.txt, and if the line matches some regular expression that looks like a key-value pair, we output the key-value pair. And now normally the RE constructor that is defined in line 1 would be invoked for every single iteration, but thanks to term rewriting macros we can optimize that. So in line 4 we say if it's again a string literal, we can do the parsing of the string into a regular expression just once and store it in a global variable g and use that variable g instead in line 6. So this implements a form of invariant code hosting. Okay, there's another thing that, oh yeah, and by the way, Perl performs the same optimization, but in Perl regular expressions are built in. In Nimrod, there's no need to that. There's no need for that. We can optimize them in the same way anyway. Okay, another detail is the equals tilde matching operator that delegates its work to a match function in line 11. So that's not the interesting part. The interesting part here is that in line 9 and 10, we inject into the invocation scope a variable marches, which is an array of strings, if the scope has no marches symbol already. So the marches array is injected and used then in line 15 implicitly. Now this is a highly controversial language feature, but it's quite useful, and perhaps not in this case, but in other cases. Okay, now the summary. We have seen how compile time function evaluation helps to optimize the code. What we didn't see is that Nimrod also has static read and static exec functions. So static read reads in a file at compile time and transforms a string literal out of it. Static exec executes some external process, captures all its output and transforms it into a string. We have seen Nimrod's declarative and imperative AST-based macros. We've seen they are both hygienic and dirty. We have seen term rewriting macros. What we didn't see is that the sub-language that defines patterns is actually quite sophisticated. So you can request that the pattern has no side effect or that some expression does not alias with some other expression. And that's pretty important to get these optimization routes right. We also didn't see source code filters, which is yet another way to produce HTML code. And we have a programmable annotation system. So the curlies and the dots that you saw are called pragmas in Nimrod. And you can define your own and transform them via macros. Okay, what we also didn't see is quasi-quoting. Here in line 4, we have the built-in quote that produces an AST for us in an easier way than dealing with the AST API. Yeah, it's pretty much obvious what it does. It produces an if not expression, then say, look, in this line, the expression failed. Yeah. Okay. Thank you for listening. We are always looking for contributions, so please check out the GitHub repository and see what's left to do for you. And if you need some nice ideas about cool projects involving Nimrod, join our IRC channel, and I can give you quite some interesting projects to do. Yeah, thanks.